Hello everybody to our last session that contains new material. Um, just to avoid technical difficulties, can anyone just confirm to me in chat that you can both see and hear me? I'll bring up
We can
something to
see and hear
scribble on.
you.
Good, good, thank you. Be nice to have a last lecture issue free. That is always the dream. Don't have that much today, so I want to revisit some things that we have done and just sort of put it together in maybe a more complicated example that's not in the book. Let's just think, how can we make this more interesting? Last time I did mention the window idea, so let's maybe start with that. Let's suppose I should actually not start. I should start with a circle. It's going to be easier to draw. Let's suppose I have a fancy window and it has a half circle top. Cheat by just erasing the bottom half. Bigger half circle fairly nicely. And then I have a rectangular bottom, say like so. This was a really good example, and I want to make it a little bit more specific with actual measurements and actual things to calculate. So let's suppose here we have actually let's make it, I'm trying to come up with something as difficult as possible for what we want to do. So let's make it interesting. Let's say the total height of the window is, I don't know, how tall is a window? Let's say 2 meters. And the total width of the window is, how big are windows? Let's say half a meter, like that, right? Then we want to find two things. We want to find the perimeter. We want to make something and put it all the way around a window. So I want to know the perimeter. That is certainly a question that has some practical possibilities. And then later on we'll do the area as well, but I'm not sure how much space I'll need. Let's just do the perimeter first. So I need to figure out all these segments, right? Everything around, and for the circle part, I just need the radius, right? That was supposed to be a curly bracket. So the radius is certainly maybe the easiest thing to find next. It'll be half of the width. So it'll be 0.25, half of 0.5. That means this, let's say, height of this half circular section is also 0.25. So if I take that off of the 2 meter height, I'll get 1.75 as the height of just the rectangular section, which I'll need. So I'm now ready to find the perimeter. The perimeter, let's call it P for perimeter, is perimeter. Let's start at the bottom. Why not? 0.5 plus, so then check, that section is included. Then the 1.75, then halfway around the circle. So a half times the circumference of a circle with radius 0.25, it's 2 pi 0.25, 2 pi r. check. And then I ran out of space, but added here the other side of the rectangle, which would be 1.75. Again, just trying to see how can I make this a little bit more interesting. But for perimeter, you still need to find all the sections one way or another. So let's do that. Our calculator and see what we get. 5 plus 1.75. So the half and the 2 cancel. So I have pi times 0.25 plus 1.75. Like so, like so. Get 4.7854, and that's done. So in terms of perimeter, there's not much more we can do here, right? Just trying to think of something we haven't covered yet in case you encounter that in one of the problems. There's a lot of problems. I certainly don't remember them all. Something with a part of a circle mixed in with something else is good. Now let's look at area. Let's call the area A. So now it's a little bit simpler, I suppose. We did have that side. We just want to calculate the area of the rectangle, area of the half circle, and add them together. The area of the rectangle will be product of the two length and width dimensions. Area of the circle, well, it's only half a circle, so a half times the area of a circle, pi r squared. So then let's calculate that. See what MathBot says. Let's do it. 5 times 1.75 plus 0.5 for the half times pi times 0.25 to the power of 2. MathBot says 0.9732 square meters. I don't really have a sense. Does that number make sense? Well, it certainly has to be less than a full rectangular window of this height and width, right? Which would be 2 times 0.5, which would be 1. I'm losing these corners by having this half circle section. So, yeah, it's in the right area. It's in the right vicinity of what I would expect, but I don't know exactly more than that. That's why we have to calculate it. But I thought this was a little bit more interesting. A little bit more interesting. Right, so that's an area question. Let me just see here. Let's go to like this, but a surface area question, which means I need to make this three-dimensional, right? I want a similar kind of shape, like a statue or a pillar or something that has rectangular, and again, this is not in the book, I'm making these up. Let's suppose we have, let's see if I can draw this. We have some sort of pillar, rectangle, make it a square base. Sure, let's make it 0.5 by 0.5. And that goes all the way up. Freehanding this. I can make dotted lines later, so I'm not going to worry about that. Which edges are at the back and which edges are at the front. That doesn't really affect my visualizing it. Oh, that line wasn't good. Then, oh no, this won't work. Never mind. Back it up. This is too hard. back it up, back it up. I want to make a circular base so that I can attach a half circle dome at the top. Yes, 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 yes. So for that, I'm going to exploit my circle tool, make it a little sideways like so. Then I want to go all the way up. Circular. Oh, that's not good. Okay, so I need to move this a little bit, or just erase the extra bits that I don't. That would work. This is what happens when I make up questions. The other one was we don't have formulas for a shape that's sort of curved with a square base. That gets complicated. So then I'll freehand the circular dome at the top, which will be a half circle. Left side's always so much easier than the right. Effect here that indicates that it's three-dimensional, and that's of course the back side that we don't technically see. So I'll erase some of it to make it. Right, there we go. So for this, I obviously, well, I'm going to give the total width as 0.5 meters and the total height as 2 meters. Just sort of extending what we did here. But so that the half circle dome can fit nicely on top, I need a circular base. Okay, I think that's all we need. So now the concept of perimeter, sort of the outside of a two-dimensional shape, becomes the outside of this three-dimensional shape, which would be surface area. So surface area is sort of the three-dimensional version of perimeter, outside. And when I go a dimension up, then this sort of goes a dimension up as well. Let's call it surface area. Surface area. Well, for that, just like before, I need to, whoa, that is a terrible curly bracket, but I'm going to go with it. I need to know the radius, of course, 0.25 like before. And I would also need to know, ooh, that is unacceptable. Bendy, like that. The height of just this cylindrical part. Well, same as before, right? I picked the same numbers. Then this top of the cylinder to the top of the half circle will be 0.25 as well. Because this is 0.25, it's all circles. All the radius sections are the same. And then I get 1.75 again. Even though my drawing makes it look like this half circle part is a little bit higher, I have to trust the numbers. Okay, so the half circle. So first one here will be the half circle dome thingy. And then we also have to cylinder portion. Half circle, surface area. So it's a half of the surface area of a sphere, which is 4 times pi times the radius squared. So 25 squared. Briefly mentioned it at the end, briefly because I can't really, I don't have the mathematical tools to derive why the surface area of a sphere is 4 pi r squared. Some things we're just going to have to believe at this level. And then I have to calculate the surface area of this cylinder. How am I going to do that? Well, let me put this in a space here. Let's make a plan down here where I have more space, because the cylinder has a bottom that's different from the side of the cylinder. So I have a circular bottom that I need to calculate the area for, and then I need to calculate the size. Let's just do the circle base. That's just a circle that has area pi r squared. Pi times 0.25 squared. You see how quickly things get calculated depending on the shape. Now, how do I visualize the side of the cylinder? Well, if I cut it open, let's suppose this is like a can that I can cut, and then I fold it out. I'm going to get a fairly long rectangle. I fold it out. The height of this rectangle will be 1.75. Let's have a little bit more space here. This arrow comes down. The length of this rectangle will be the circumference of the circular base, 2 pi r. Cut it open, pretend it's a can or something, and I fold it out. Then I get a rectangle along the side. So the area of that rectangle is just the product of those two. In this case, the radius is always 0.25, and then I have another 0.75. This goes in there. But perhaps let's do it in pieces so that we can hopefully minimize calculator mistakes. If I try and do too much all in one, more likely to make a calculator mistake. So let's see here. Let's just do that half spherical dome, and let's call it A, and the other part will be B. I just need to give it a name because this is going to be an ugly decimal number, right? All right, so let's do that. So I have 0.5 times 4 times pi times 0.25 squared. Says something that you can see if you can verify. I'm just gonna put it over here. My space management is not right today. It's part of it. That's the dome. So see if you can get that same answer. Then for the cylinder portion, I'm going to call it B, just so I can use the memory function of my calculator and not have to type all the decimals again. Simply a matter of convenience, though you can type all the decimals all the time. Don't want the memory function. Okay, so this one comes, excuse me, this one comes in two parts. I'll just do the whole square bracket thing right away. B right, let me do this. Pi times 0.25 squared plus 2 times pi times 5 times 1.75. And then we get the number I left space for this number, 2.9452, and that's my other one. So then finally, I'm going to write finally because I'm happy to be at the end here. Surface area is those two numbers multiplied together. Don't use the rounded ones, of course. See what that is? But luckily I assigned variables to this, so it's easy to do. 3.3379 surface area square meters. Well, hopefully that was fun. Certainly more interesting. Definitely more interesting, which is what I was aiming for. So I think this is sort of at the high end. Certainly we can handle it. We just have to section it and do it in pieces and systematically get to the answer, right? But that's true for everything. That's the underlying theme of really any math course. Just break it up into manageable pieces and slowly build towards it. Okay. So when I think about these two-dimensional shapes to three-dimensional shapes. 2 dimensions, we have the concept of the outside, the perimeter. When I go to 3 dimensions, that extends to the concept of surface area. When I look at 2 dimensions again, we have the concept of area, the area of this inside. If I extend that, so the inside, right? If I extend that to 3 dimensions, it extends to the concept of volume. The last thing we have to do is talk about briefly the volume of three-dimensional shapes. Volume. Now the concept of volume is the same as the concept of a length measurement where you have a unit and you're trying to see how many of that standard unit length can fit into your length that you're measuring. Concept of area, you have a little standard unit square, you're filling the shape with that, and that's the area. Volume is no different. You just have one more dimension. You have a standard 1 by 1 by 1 cube, maybe centimeters, whatever your standard unit is that you're working in. And given a three-dimensional shape, you're trying to see how many times does the little cube fit in and fill this shape. Now in this case, we're going to use a cubic meter unit. Units can change, but you still have this 1 cubic unit, volume unit. So the concept of filling it with a certain number of these units is the same. Now, to make this simple, because volume can be very complicated, if I let the shapes just get a little bit fancy, we'll mainly stick with a regular, or a prism. It doesn't have to be regular. Prism. So let's remember what a prism is. It doesn't have to be regular. The sides can be much higher. But a prism, in the mathematical sense, is, now you can define this in many ways. You have a base, and then you have perpendicular sides, well, on the side, and then the top is the same as the base. That's a prism. Think of it as a box. You maybe have a square base, could be a rectangular base. All sides go straight up, maybe high. I can't draw fast. pretty high up. That's okay. We don't ask for regular anymore. Extending it a little bit. But this bottom base shape is exactly the same as the top, and then everything is perpendicular. We can also have, like we sort of saw here, the cylinder part is also a prism. So this could be maybe a square prism. It doesn't specify it uniquely because I can have a height that varies. Or I can have a circular base. Now I'm freehanding this, so of course it's not going to look right. But you get the idea. I like freehanding it sometimes just for practice. Circle base, circle base. This can be called a circular prism. Or more casually, a cylinder, right? Cylindrical can, you see it in stores. You see shoe boxes. These shapes are pretty common, and that's why they are included in the elementary school curriculum. But of course, I can be much fancier, right? I can make this base and still have simplicity. I can make it any polygon, really, right? Now we can keep it and make that base polygon nice and regular, and we don't have any significant problems, because in our semi-regular polyhedra groupings, one of those groups were regular prisms, where the base could be any regular polygon. There are infinitely many of them. We're just extending that a little bit to allow for flexible height. The height could be anything, so the sides don't have to be squares. They can extend to rectangles, but we still have a lot of structure here. So because we're sticking to our structure, the surface area calculations we can certainly do. Let's say here, must be able to calculate surface area for these. And the new part is the volume. Now the volume is really quite simple, and especially in the square case, it's not that hard to go from the basic concept of volume fitting in units to the volume formula, which is the area of the base times the height. Area of the base times the height. That is going to be the only volume formula that I'm interested in working with. And it extends to any prism. This is only for the prism, right? Prisms only. But circular prism, square prism, any polygon based prism, it's all good. Okay, so we now wrap this up. Just want to practice this formula, keeping in mind that you should be able to answer the surface area question for all of these as well. Make it even more interesting by sort of attaching pieces, but simple shapes in isolation, certainly. All right, so we have this proposition just says how to find the volume. We have exercise 17.6, 3 examples to calculate. They ask just for the volume. Certainly, we should be able to practice the surface area as well. So keep that in mind if you're looking for more questions. Surface area, what should I be able to do? These are definitely good ones as well. Done. Well, we have done one here, potentially. So the first one in exercise 17.6, triangle out. They're not numbered, but I'm numbering them. Triangular prism with side length 2. Now, I'm not making the base super difficult because I won't be able to height. Oh, they say it's regular. Okay, so let's not make it too high. They did say it's a regular prism, so the height is the same as the side length of the triangle. Just to make it even easier. It's too easy. Just be aware that the height can length 2 units. I'm going to make it centimeters just so we can write down the unit of the volume answer. Why is my prism so low? I don't know. Volume D. Now I need the area of the base area times the height. So the area of the base, my regular polygon formula, even for the triangle. Remember what that was? I hope we do. Side length squared times the number of sides in my polygon, which is 3 over, times tan of 180 degrees over number of sides of my polygon. That gets multiplied by the height, which is also 2. But the height could be different, right? So let's see what we get when we calculate this. 2 squared is 4. Oh, wait. 2 squared is 4. Cancels with this 4. Makes my calculation a touch easier. Why not do that? So I have 3 divided by 10 degrees 180. And we've done this a few times now, right? And then times 2 for the height. Get that times 2. And we get 3.4641 cubic centimeters. This one has a square centimeter unit. This one has another centimeter. So I have 3 centimeter units for centimeters cubed. Should be pretty standard stuff by now. We've seen the formula. We've practiced the formula. Should be pretty straightforward. Practiced our calculator. Not much to it, which is good at the end. A square prism with side length 3. Oh. That's a little boring, but okay. 3. Let's call it centimeters. It's a cube. Do I know the volume? Volume is 3 cubed, which is 27 cubic centimeters. But I think my goal here was just to verify that this fancier way of looking at the prism will cover the basic, simpler shapes as well. Say the base area times the height. Let me just go overkill here by using the same formula, getting what this is, just to show it still works, it still covers it, everything is the same. The base is a square, it's a regular quadrilateral, side length squared times number of sides, tan 180, I know it's overkill, over 4, times the height, which is 3 again, just to show you. I'll still get to 27. This is not an exception or anything. Calculate the whole thing exactly like that. 3 squared is 9 times 4 divided by 4 divided by 10 is 1 80 if I can learn how to type. That times 3. Oh, big surprise. I get 27 again. I know you were shocked. Not that I would use this. I would think, well, is this a simpler shape that I can use a simpler formula for? Yeah, it's a cube. Okay, let's not bother with this then. But I just want to verify that even if you don't see that or you don't remember how the simple formula for a cube looks, our formula for a regular polygon would still work. But it is unnecessary, right? Then you run the risk of making calculator mistakes. Yeah. Scroll. That's always nice. There we go. Number. Pentagonal prism with side length 4. Ooh, I can draw it. Practice. I need to practice. Position my pentagon here. That. Maybe. Could be. It's the drawing. Come, unless you are a natural artist, which some of you may be, it by itself, right? You have to practice. I have to practice a lot. This is the result. So, yeah, I know. Volume is area of the base, the height. So, area of the base, well, it's pentagon. Regular pentagon, side length squared, number of sides. 4 is always a 4. Tan of 180 degrees over sides, which is 5. Then times height, which is also 4 because it's regular. Regular. Could have a different height, but it doesn't in this case. Now, yes, I can make this a little bit simpler here. I have one of these 4s cancelled with that bottom 4, and that's pretty much it. Let us see what this is. Four times 5 divided by 80 divided by 5. Don't forget that last times 4. And we get, did I do that? 110, 0, 6. Right, so I don't think that's anything crazy. One last little thing is when we look at shapes like this, I want to calculate the volume of this as well, right? So a sphere or a part of it can be in play, and I want to know the volume of the sphere. That's our last thing. Again, I can't really prove that. Need some calculus to make it probably the most efficient way. Get this formula, but volume of a sphere of radius r, radius r, this other line is to make it three-dimensional, is 4 over 3 pi r cubed. See the cubed for the 3 dimensions? 4 over 3, just memorize it. Now we can go to this guy and calculate its volume. I'm actually going to do it right beside here. see the shape. We're done with surface area. We don't need to screen. Get rid of it all. Now I want volume of this dome-like statue thing. Which means, of course, I'm going to call V. I have two sections here. I have the dome, and I have the cylinder portion. And I'll add them together. Dome is a half of a sphere. So it's a half times the volume of a sphere. 4 over 3 pi, squeeze it in that much. Pi times radius cubed, so 0.25 cubed. Hopefully you can read that. Plus the volume of this cylinder, the circular prism, which is area of the base pi r squared times the height. Done. Do it all in one go. Our last calculation. Let's make it a good one. Here we go. 1/2 times 4 over times pi times 0.25 cubed plus pi times 0.25 squared times 1.75, and we get 0.3763 meters. Big meters. Or could be. Don't really know, right? Seems a little small, but it's hard to say. I could maybe extend the cylinder all the way up and say that, oh, well, it has to be smaller than the area of the cylinder, the big cylinder, right? Because I'm losing some space by having the circular top. And the area of this cylinder will be area of the base circle times 2. Area of the base circle will be pi r squared, so pi times 0.5 squared, and then times 2. Let's see. Pi times 0.5 squared times 2. Area of, oh, I lose a lot. That seems unlikely. Pi r squared maybe. Well, of course, being my last example, I'm not surprised if I did make a mistake. Let's just double check this calculation. We had the circular dome, which had a radius of 0.25. It's a half sphere. The volume of the sphere is 4 over 3 pi r cubed. And I then half that, plus the volume of the cylinder, which is area of the base, pi r squared, times the height, 1.75. Very good. Please make sure and confirm it. I'm skeptical, maybe. Maybe I want to confirm it again. Since I have 4 minutes, I need to stretch the time. Our last lecture, I need to give you the full experience. I'm going to calculate again. Practice my calculation. You can do it too. Even though it isn't the correct answer. In a test, you won't know. So in a calculator double check, you have to really sort of be objective. Do not run the risk of making the same calculation mistake that you won't realize you're making, right? So I want to step away and really think, how did I set up this calculation? Does that look right? And then, as if it's for the first time, calculate it again. I'm going to do it. Not make a mistake in the exam. Here we go. Half, which is 0.5, times 4 divided by 3 times pi times 25 cubed plus pi times 0.25 squared times 1.75. Try to be as objective as I can. I get the same answer, so I'm now a little bit more confident. But it's hard to sometimes, especially when you're going between length calculations and area calculations and volume calculations, to really get a sense of, is that a good number? Does that number make sense? Oh, I don't really know sometimes. And to double check a calculation, you sort of have to sort of reset everything. Otherwise, you could just make the same calculator mistake again and you won't notice it. So, okay, so you're saying you're getting 13.9248. That seems a little big, very big. And that can happen, right? So the only thing I could really do to get a sense of, is this reasonable? Well, my answer should sit somewhere between just the base, just the bottom cylinder, because I'm adding to that. Between that, the cylinder of a height 1.75, and the cylinder with a height 2 meters. Somewhere in between is my volume. And we calculated the sort of the overestimate using the 2, we calculated as 1.57. So it's definitely below 1.57. So then when I get a number like 13.9, I'm like, okay, that can't be right. And then I need to reset everything and see objectively what could I have done wrong, especially if I keep getting it. But let's end the video there, and I'll stay behind to talk about that, and we can maybe figure it out. All right, let's just double check our schedule to see where we are, what is coming up. We have finished all the material for the course. Hooray! And now it's just a bunch of Q&A sessions on the way to our quiz on Tuesday. Are there any questions at this stage? All right. Then I will maybe see you in a Q&A session, maybe not. Use them as you need to. And we are very close to the end. Until later. Thank you.